We will start in a few seconds. So a very quick thing, I sent you guys a survey to know what is your preferences for help session time and also for the quiz time. I only got 5 responses and we are like 25 in the class. So if I didn't get any other responses by the next week, I would like rely on these 5 responses and make my help session on Thursday and the quiz time on the Friday. So please make your preferences so I can make decision about the help session time and the quiz time. Yeah, and for the Canvas page, I think right now our modules is up to date. We have everything by day here, and you will have the homework assigned. I just found somebody sent me an email yesterday with the wrong due on date for homework 2. It was June 18th, so I changed it to June 21st. It's a 2-problem homework, and also homework 3 is also another 2 problems. Each problem shouldn't take like 15 to 20 minutes, so it might take less than this. So I think you will be able to solve homework 2 and homework 3 based on the knowledge from the last 4 lectures. So does anybody have any questions so far before I start our new topic?
I just had a question about the quiz.
Okay, go ahead.
So what chapters specifically is that quiz going to be over?
Today's quiz?
Yes.
It will be the first 3 lectures, the rectilinear motion and the erratic motion. Okay. And also there will be some general questions not related to motions, like test your background about how you calculate angles and this stuff.
Sure, thank you.
All right, yeah. So let's get started with continue our curvilinear motion with new coordinate system, which is the polar coordinate system. As you know from your previous background, that there is multiple systems that can be used to describe the particle in space. One of them is the Cartesian, which is the XYZ coordinate, and we also have a cylindrical coordinate system if the particle mass is on a cylinder or have a spiral like this. Oh, sorry. Have a spiral like this. So the particle is moving on a circle, but the Z is keep changing. So we best use the cylindrical coordinate system, which is described by R, the radius of the circle, and the theta, and then the Z. Sometimes the particle is moving on a spherical path. So it's better to describe it with a spherical coordinate system, which R and theta, which is the angle from the x-axis, and phi, which is the angle from the z-axis. However, in this class, we will not be dealing with 3D, so we will be all of our motion will be in the XY direction or in the plane. So we will be using R and theta, and it should be the same if you neglect the Z from here and the phi from here, so you will still have R and theta, because most of the motion will be like a circular motion or in plane motion. So all what you need is just R and theta. So let's see how to describe the motion using the polar coordinate system. So if this is our base and it's a curved base and our particle at this location, so we should have an origin to measure the position of this particle. So this position is described by r vector. So the r vector is the radial in the radial direction, and it started from a certain origin, which is predefined origin, and goes up to the particle at this location. So this is the r, and here's the direction of the r vector. And the second dimension is the theta, which is the angle measured from a datum to the r vector. and the theta direction is perpendicular to the r direction and in direction of increasing theta. So theta should be either in this direction or in this direction. So as I have the particle is moving on this path like this, so this is the direction of increasing theta. So this will be the theta direction. So it is not this one. But if the particle is moving in the other direction, so the theta, the direction of theta will be in this direction. So let's stick with the first one, and let's say that this is the theta direction. So this is how the r theta look like. If you recall from the last time, we had a tangential component. So the tangential component was look like this, and this is the tangent direction, and the normal direction is perpendicular to the tangent direction in the direction of the center of curvature. So this is the difference between the polar coordinate system and the tangent and normal coordinate system. So let's delete this for now. And let's stick with the polar coordinate system. And let's first describe the position. So for the position, is described by r vector, and the r vector has a magnitude r. So the magnitude r, which means the r vector in between the determinant. So this is the magnitude in the r direction. So we have the magnitude of all of this path in the r direction plus 0 in the theta direction. So we don't have any component of r in the direction of theta. We might like write this r u r hat plus 0 u theta hat. So both should be the same. Sometimes it's more faster to write it like this, r and 0. We know that the first one is in the r direction, and the second one is in the theta direction. So this is the position vector, and let's make some definitions. So r is the radial axis, goes from the origin to the particle, and theta is the transverse axis to r in the direction of increasing theta. So we don't have to write them. So just what is the r and what is the theta. And let's write the velocity. So as you recall from the last time, the velocity is always in the tangent direction. So it has a vector like this. So this is the v. But if we want to describe v, and so this is the v tangent, and there isn't a component of the velocity in the normal direction. So all the velocity component is in the tangential direction. So based on the new coordinate system, which is r and theta, we will be having a velocity in the r direction and a velocity in the theta direction. So we will have vr and v theta. So velocity. So v vector is equal to vr as a magnitude in the direction of the u r hat plus v theta in the direction of u theta hat. So we have two components because we are dealing with r and theta. So let's find how can we get these components. From the versatile principle, we know that the velocity is the time rate of a change of the position. We can write it like this. So we have this as 0, so we'll have to differentiate this component, or differentiating this component. So here, let's make this a little smaller. V vector. And let's see how is the dr dt changing. So if the particle is here, so we will be having let's make this smaller. So this will be the new position, and this will be the new r vector, and this will be the new theta. So let's see how the r is changing over the time. So if we took the derivative of the this quantity, so we have both, could be both r and ur is changing. So what we will do is just like differentiate the first dr dt and keep ur hat plus dur hat dt multiplied by r. So the derivative of the dr dt will give you r dot. As we know, right now we need to know what is the value of this quantity. So let's write this like this. Here is the theta, here is the r, this is this too, and let's have the change. So let's say that we took a unit vector like u r hat, and this is the direction is u theta hat. And at here, so this is the direction of the u r hat dash, and it will be like this. Let's make it right. This is the u theta hat dash. So this is how the ur is changing. The direction is changing. And let's put this as u theta. All right. So what we want to know, we need to know what is the value of the u dur hat and what is the value of the du theta hat. So how can we get this? So we know that the change in the angle is very small, which is like assuming that this is a very small angle, d theta. So this will be d theta and this will be d theta. And if we want to calculate the value of the dur hat, so it should be equal to the magnitude of this length, which is the magnitude of the ur hat multiplied by d theta. And in the direction, as we know that this is a perpendicular to the ur, so it should be parallel to the u theta hat. So we know this is in the direction of the u theta hat. So this is the unit direction of this value. The magnitude of this value, as we know, this is a unit vector. So the magnitude of the unit vector is always equal to 1. So dur hat will be equal to d theta in the direction of u theta hat. So if we want to take the time derivative of this, so dur hat dt will be equal d theta dt multiplied by u theta hat. So we can write this as theta dot u theta hat. Similarly, we can calculate the d theta hat. So if you want to calculate d theta hat, so it will be equal to the magnitude of u theta hat multiplied by d theta. In the direction, if you look at this direction, you will find that it's in the negative direction of the ur hat. So this is going this way, but ur hat is going this way. So it will be in the negative direction of the ur hat. And the magnitude of this unit vector is equal to 1. And you finally will end up with d theta in negative value in the ur hat. If you want to take the, this is the d u theta hat because we are calculating the value of this. If you want to calculate the time derivative of the du theta hat by dt, you will have dt here. So it will be negative theta dot u r hat. So we got this value and this value. So let's get back to the velocity. So we know right now what is the value of the ur dt. So if you came here, it's theta dot. So let's plug it in the equation. So the v vector will be equal to r dot ur hat plus, here is the theta dot, and we have r here. So this will be equal to r theta dot in the direction of u theta hat. So right now we know what is the value of the VR and what is the value of the v theta based on this equation. For the acceleration, so the acceleration A will be equal to AR in the direction of the U R hat plus A theta in the direction of U theta hat. So based on the tangent normal coordinate system from before, you know that you will have a tangent acceleration. So you will have like a tangent acceleration in this direction, and you will have a normal acceleration in this direction. But right now we need their projection in the direction of R and the direction of theta. So right now we will have them in terms of R and theta form. So if we want to calculate this, we will go also back to the Versta principle that A vector is equal to the time rate of change of the velocity. So if we want to differentiate this, so it will be a long differentiation. So because you have R dot here multiplied by UR and R theta dot multiplied by U theta. So let's differentiate the verse term. So the verse term here, it will be equal to, if you take the time derivative, let's put the velocity here, R dot UR hat plus R theta dot in the direction of U theta hat. So it will be the derivative of the first one with respect to t. It will give you R double dot in the direction of the UR hat, and then derivative of the second will be R dot multiplied by DUR hat dt. So we are done with the first one. Let's do the second one. So it will be R dot multiplied by theta dot. So we'll differentiate the first one with respect to t multiplied by the other terms, plus the derivative of the second term. So it will be R double dot in the direction of the U theta hat plus this multiplied by the derivative of that. So it will be R theta dot du theta hat dt. So after you plug in the values of this here, it's theta dot u theta hat, and plug the value of this, which is this, negative theta ur hat, and then do separation of variables to put the things that have ur and ur together, and the things that have the terms that has u theta and u theta together. You will end up with the acceleration will be equal to r dot double dot minus r theta dot square ur hat plus r double dot plus 2 r dot theta dot in the direction of the u theta hat. So this is the term for the velocity, and this is the term for the acceleration, and you should find these equation in the sheet that you have for the dynamics equation sheet. You don't have to remind this equation, you just like use them directly, but here how we can derive them from Versta principles. And actually, if you have if you want to solve let's say that there is a playground that has a spiral slider, and there's a kid here is moving like this, so you can add a z term to all of this equation. So you can for this equation, you can add plus z in the direction of uz, because we have the z direction is a linear direction. So it's just like the position z in the direction of uz hat, and if it's for the velocity, it will be z dot in the direction of the uz hat, and the acceleration, it will be z double dot in the direction of uz hat. This is if we are working with 3D dynamics, so we will have to add the third dimension, which is the z. All right, so let's now see a quick example how this equation look like if we have a body is moving on a circle. So if I have a circle like this, and it has radius r, and there's a particle is moving on this circle using this radius r, as we can see that r is constant, so r is not a changing with the radius. So if r is constant, like let's say circle, if r is equal to constant, so r dot is 0 and r double dot is 0. So if we substitute back in this equation, so the UR will be equal, the VR will be equal to 0, and you will have the r-theta dot component. So the V will be equal to 0 in the UR direction plus the r-theta dot in the u-theta direction. And if you calculate V, it will be r double dot is equal to 0, so you will have negative r theta dot square in the direction of the u r hat, and here you will have r dot is equal to 0, but you will have this term. It will be r theta double dot in the direction of the u theta hat. So this is how the equation look like if you are moving on a circle. So all your velocity, so if we are thinking like this is the how is the theta increase, so this is the direction of r and this is the direction of theta, so all the velocity component is in the theta direction, so it's in this direction. So this is v theta, and the acceleration you will have a 1 in the negative ur direction, so you will be having the AR in this direction and the A theta in this direction. So it's kind of similar to the tangent normal components. So it end up with, because in the circle, the tangent, I mean like the theta direction is the tangent and the r direction is in the negative direction of the n hat. So this is how it looks like, which is like similar to the tangent normal direction. So if we want to see some example how the r could change over the time, so here's like shows an example, like if you have, I think we will solve this. Let's see what we can do in like 5 minutes from now. So this shows a rod bend at this location and has like a nail in this, like a nail and a pole in this direction, and you will have like a collar or a nut on this bolt. So the r is keep changing over the time, so or over the theta, and theta changing over the time. So this is how we measure theta. So this is the datum, and this is how the theta increased, and also the r is keep changing with theta. So this is how the r as a function of theta. So what I do in this problem, he want me to calculate the velocity and acceleration vector at this instant, where theta is equal 120 degree and theta dot is equal to 0.1 radian per second, and here's a theta double dot and give me r. So I will do further calculation by calculating r dot. So I will have to differentiate this term with respect to t. So if you differentiate it, it will give you 2 cosine theta, but I'm not differentiating with respect to theta. If I'm differentiating with respect to theta, I will keep it like this. But I'm differentiating with respect to t, so I will have to take the derivative of the term inside. So it will give me theta dot. And if you take the second derivative, so you will have to differentiate this another time, it will give you 2 sine theta multiplied by the derivative of this theta, so theta dot multiplied by another theta dot will give you square, plus the derivative of the second term multiplied by the first term. So it will be 2 cosine theta, theta double dot. So you got the r and r dot and r double dot, and you have the theta and theta dot and theta double dot. So you can substitute in these equations 2 sine 120, and you can get this value. And also you can substitute in this, and you have 2 cosine 120 multiplied by theta dot, which is 0.1, and you can get this value. Similar here, you can negative 2 sine 120 multiplied by 0.1 square plus 2 cosine 120 multiplied by theta double dot, which is negative 0.04, and we can get this value. And then we will go back with these derivatives of theta and r and back to the equations here, the a and the v, and substitute, so we will get the v and a vector. So I will stop here now and I'll solve this problem in detail next time. I'm just like giving you some insight how could r and theta changing, like you have like a rod like this and it's moving in a circular direction, like has an r and theta, and r of the particle of this particle is keep it changing as theta is moving. And this is also another example. We might solve it next time. So does anybody have any questions? I will like solve 2 examples in the lecture of Monday, next Monday. If you have any question, just go ahead and say it. All right, with this, I think you will be ready to start your Versta quiz. You will just like basically go to your Canvas, and I think if I go here in the student view, and you will be able to find quiz 1, and it should open at 10:15. So just like 4 minutes from now, and I will be online. If you have any technical difficulties, just like send me an email. If like you have an internet crash or any issues, just like send me an email and I will fix it right away. All right, see you guys on Monday.
Thanks.
Thank you.
Thanks, everyone.
Thank you.
Thank you.
Thank you.